Imagine a Wi-Fi connection, but not the kind you're used to. Imagine a cosmic network that works everywhere in the universe, spanning across galaxies and vast cosmic distances. A connection with no router, no password, absolutely no lag, and no monthly fees. This isn't some far-fetched science fiction dream. It's the mind-bending reality of quantum entanglement. It's the universe's own instant, invisible connection, a fundamental aspect of reality itself. Entanglement mysteriously links tiny particles, even at enormous separations. It dictates that what happens to one entangled particle instantly affects the other, regardless of the distance separating them. It's truly bizarre. It's the secret sauce behind the promise of quantum technology and computing. This strange phenomenon even baffled the great Einstein, who famously called it spooky action at a distance. Picture two particles, intrinsically linked from the moment of their creation. Imagine one residing on Earth, while its entangled partner is light years away in a distant galaxy. If you measure one, you instantly know the state of the other, as if they were communicating faster than light. But here's the kicker. There's no signal traveling between them. It's a shared existence, a connection woven into the very fabric of space-time itself. Entanglement profoundly challenges our most basic ideas about reality, locality, and the nature of distance. It uncovers a deeper layer of connection, a quantum fabric woven into the very structure of the universe. The universe is far weirder and more deeply connected than we ever could have imagined, pushing the boundaries of our understanding. So, welcome to the universe's weirdest Wi-Fi, a quantum network that defies explanation. Let's make this less abstract. Quantum entanglement can be a tricky concept to grasp, filled with complex equations and mind-bending ideas. But at its heart, it's about connection, a connection that transcends space and time. Imagine two cosmic twin dancers, perfectly in sync, moving as one across the grand stage of the universe. Their movements are mirrored, their fates intertwined. You send one to Earth, carefully packaged and delivered across the vast expanse of space. The other, to the Andromeda, galaxy millions of light years apart, a journey that would take light itself millions of years to complete. Open the box on Earth, your dancer spins clockwise. You observe its rotation, noting its direction with precision. Instantly, without any signal or communication, you know the other is spinning counterclockwise. It's as if they're connected by an invisible thread. No messages, no delay, no known force could possibly transmit this information faster than light. Their connection is quantum entanglement, a bizarre and fascinating phenomenon that has baffled scientists for decades. Now swap dancers for photons, tiny packets of light, the fundamental building blocks of electromagnetic radiation. Entangled photons have linked properties, polarization for example, that are correlated regardless of the distance separating them. Measure one, and the other's state is set instantly, as if the universe itself is keeping score. Before measurement, neither has a definite state. Their properties are undefined. They exist in a fuzzy superposition, a blend of all possibilities, until the moment of observation. The act of observing one collapses both, forcing them to choose a definite state. And this happens instantaneously, no matter the distance, defying our classical understanding of cause and effect. This isn't like finding out which glove you picked from a box, where the glove was always either left or right. Here, the outcome isn't set until you look. The act of observation creates the reality. Entanglement is a real, tested phenomenon, confirmed by countless experiments in laboratories around the world. It's not just a theory, but a fundamental aspect of the quantum world. It's a cosmic dance that defies our everyday logic, challenging our intuitions about space, time, and reality itself. The universe, at its core, is stranger than fiction, filled with mysteries that continue to inspire and perplex us. And this dance is happening everywhere, all the time, shaping the very fabric of reality at the smallest scales. Even Einstein thought this was impossible. He called it spooky action at a distance. To him, nothing could travel faster than light, not even information. He believed particles had hidden instructions set from the start that determined their fate. In 1935, Einstein and colleagues proposed the EPR paradox, arguing quantum mechanics must be incomplete. They thought there had to be hidden variables, local preset rules. For decades, this was a philosophical debate: is the universe truly spooky, or is there a hidden reality? The physics community was divided, waiting for a way to test these ideas. The stage was set for a scientific showdown. Enter John Bell in 1964. He created a mathematical test, Bell's theorem, to settle the debate. If Einstein was right, entangled particles' correlations would never exceed a certain limit. If quantum mechanics was right, those correlations would break Bell's limit. Bell's theorem turned philosophy into experiment: create entangled pairs, measure them, and see what reality says. The experiment was simple in concept: measure thousands of entangled particles, compare results, and check Bell's inequality. If violated, the universe is truly non-local and spooky. Bell handed physicists a tool to probe the nature of reality itself. The great debate was about to be settled not by argument, but by evidence. The implications were massive, reality itself was on the line. The countdown to proof had begun. After Bell, physicists raced to test his theorem. Early experiments in the 1970s hinted at quantum mechanics being right, but had loopholes. In the 1980s, Alan Aspect's team closed key loopholes, showing clear violations of Bell's inequality. Later, in 2015, loophole-free tests sealed the deal. Entanglement is real, and the universe is non-local. In 2022, the Nobel Prize went to Aspect, Clauser, and Zillinger for their pioneering work. Their experiments proved entanglement isn't just theory, it's a controllable, practical phenomenon. This work laid the foundation for quantum technology. The universe really is as spooky as quantum mechanics claims. Entanglement moved from philosophical curiosity to technological tool. The quantum revolution was officially underway. So, what can we do with entanglement? It's the backbone of a coming technological revolution. Imagine a quantum internet using entangled particles for perfectly secure communication. Quantum cryptography means any eavesdropper is instantly detected, making data unhackable. Quantum computers use entanglement to link qubits, solving problems classical computers can't touch. Hundreds of entangled qubits could transform medicine, materials, science, and AI. And there's quantum teleportation, transferring the exact state of a particle across distance. No information actually traveling in between. While we're not teleporting people, this is a key step for quantum networks and distributed computing. Entanglement is turning science fiction into science fact. The quantum world is opening up new frontiers. The future is entangled. So, after all we've explored, after delving into the bizarre and beautiful world of quantum entanglement, what does all this mean for us, for humanity, for our understanding of reality itself? Quantum entanglement reveals that the universe isn't just a random collection of separate, isolated things, each existing independently. It's a deeply interconnected whole, a web of relationships woven across space and time. Imagine two particles, separated by galaxies, light years apart, and yet they can share a single, unified existence. Their fates intertwined in a way that defies classical physics. That fundamentally shatters our ingrained sense of separation, the illusion that we are all isolated individuals. Are we too, unknowingly, part of this vast invisible network, connected to everything else in the cosmos in ways we are only beginning to understand? Perhaps the universe isn't so much like a cold, unfeeling machine, governed by rigid laws, but more like a living, breathing web of relationships, constantly evolving and adapting. Even Einstein's initial skepticism, his resistance to the implications of quantum mechanics, ultimately pushed science forward, forcing us to confront the limits of our understanding. But the accumulating evidence, experiment after experiment, revealed a deeper, far more mysterious, and interconnected reality than he could have imagined. Ultimately, science is about questioning everything, even our most deeply held, most basic assumptions about how the universe works. The stars we see above twinkling in the night sky aren't just distant, isolated points of light. They're integral parts of a vast cosmos, intricately woven together by invisible threads of quantum entanglement. Quantum entanglement invites us all, scientists and non-scientists alike, to stay relentlessly curious, and to stand in awe and marvel at the profoundly connected universe we all inhabit, a universe far stranger and more wonderful than we ever imagined. The quantum world is calling to us, beckoning us to explore its mysteries. So let's answer that call, and let's keep exploring, pushing the boundaries of our knowledge and understanding.